Lots of us played with dinosaur models as kids. Now these scientists are flying them through a wind tunnel. I'm Jen Markham on Buzz 60. Researchers at the University of Southampton built a full-scale model of a dinosaur called a microraptor, complete with actual feathers on its 5 wings. That's right, 5 wings. The scientists built the model to see if the unusual creature, believed to be the first 2-footed dinosaur to have feathers, could actually fly despite its odd leg and wing position.
So what we're looking at is, within the range of movement that we think is possible, how the aerodynamic performance varied.
Sure enough, the wind tunnel showed at least the Microraptor was a good glider.
So understanding how it flew is really important to know how flight began 150 million years ago.
I love the idea of testing the aerodynamics of dinosaurs. Next, let's get that big old brontosaurus in the wind tunnel. Buzz 60. Now you know, pass it on.
All right. 5 wings. Looks like me it has 4 wings and a tail, but anyway, so what else we got here? So we've been talking about dimensional analysis and experimental analysis. And so I think there is no sound on this, so I'll turn it off.
And so we came ready to play ball, and I just want to say, whoever steps in our way, let's have a showdown. We're out here ready to fight, and once you enter these doors, you're locked in. You know, we all came out here ready to fight. All right, buddy,
you're out of here. I wonder where the noise is coming from. So this is actually off. And so we looked at the Tacoma Narrows Bridge before. And so this is another idea of wind tunnels in terms of testing structures. A very famous, this is not from this famous wind lab at the University of Western Ontario in London, Ontario. A guy by the name of Alan Davenport was kind of a luminary in this. And the idea is that you put a structure inside the tunnel. Turn the noise on, and you measure the response. You can measure the forces that are applied to the structure, or if you're able to match, for instance, the stiffness, the elastic properties of the structure, to the real structure by scaling in the same way that we've talked about the fluid forces, Reynolds number and Euler number especially. The Euler number is the one that applies the forces to the bridge. The Reynolds number that makes sure that we have the same equivalence in terms of the flow regime. And you measure the forces. You measure the forces, and also in this case, you look to see whether you also match the dynamics of the excitation of the bridge. We talked about Kármán vortex street, the idea that you get shedding top and bottom from around this cylinder. So as air goes across the top of this bridge, it sheds an eddy from the top, and then the bottom, and then the top, and then the bottom. And these go down as a street, a vortex street. And every time it gets shed, one of them pings the bridge. And it pings it first from the top, pings it from the bottom. And so if the rate at which it does that, just like a ruler, if you bend a ruler over here and twang it, or like a guitar string, it has a characteristic frequency. If the excitation of those shedding vortices is at just the right note, then it will, as a result of that, give it this impetus, it'll pull it apart. And so we can look at that again here. This is an interesting video looking at flutter at a glance. Flutter being aerodynamics, the vibrations of structures. I'm going to turn the volume off. And so the famous Tacoma Narrows Bridge, it was just not a high wind, it was just a steady wind that blew across it before people realized the ramifications of it. And it's being shed off the downwind side, and as a result it's just putting it in twist motion along the length of the bridge as well, and ultimately it pulls itself apart. And so that was a real live example, but these these are all wind tunnel examples of doing the same thing. Looking at and also live versions of when you put a structure in motion where the resonance of that structure is exactly the same as the excitation of the wind that is driving it, then you get an unfortunate result. I guess there's still more to come. This is an airfoil bucking backwards and forwards, wings being twisted, glider wings having some characteristic mode. Looks like a 747 in a wind tunnel. Yeah, it is a 747, isn't it? some kind of dual delta-wing warplane, fighter plane. And so actually it's quite amazing, isn't it, when you look at it. Of course, you probably don't want to be on a plane when it does this. I always get nervous flying on 737s because they have a couple of crashes that aren't very well explained. One in Pittsburgh, actually. 15 years ago, all of a sudden, just flying along, perfectly fine, blue skies, coming into land, and then all of a sudden, it was buried in the ground. And I've been on a 737 where you go through a bit of buffeting, and you can feel there was something related to the controls on the tail, and I think there's all kinds of remedies in terms of what pilots do when that happens to take care of it. But I presume in newer models it was solved, the issue, but I always look at the planes that I travel on when I book flights, and tend not to travel on 737s for that reason. Real life flutter, I guess in this case. Also, I'll mute it. I think this is talking about the A380, the European, the EADS Corporation, the Airbus Corporation's answer to the 747. It's about the same capacity in terms of a large aircraft. Passenger aircraft probably takes close to 400 people, except instead of a 747, just the double decks are on the front part of the plane. This has double decks all the way through it. And so part of the airworthiness tests for any plane, any passenger plane, maybe any plane, I'm not sure, is to go through conditions where you try and make it flutter to see that it can survive flutter. So the one event apparently where the test pilots wear parachutes, as you see. So it's kind of interesting situation for that. So maybe we won't go all the way through this, but basically they take it up, they go up high, and they dive to be able to get it progressively closer to the speed of sound. We've talked about dimensionless numbers. The Mach number is a dimensionless number, which is the ratio of your speed to the speed of sound in that medium, typically air. So it's typically 700 miles an hour, 600 miles an hour. So you can do the calculation. If you see a lightning strike, and then you count how long it takes for you to hear it, you can do the calculation of exactly how far that lightning strike is away from you, from knowing the speed of sound. And so they go up and they try and push it to its limits and hopefully survive and bring it back down, and that's it. So yeah, I guess everyone's happy, clapping hands. And I don't know whether we want to watch this or not. I think this is probably the same. No, it's too long. Sorry, but you get the idea. And so all of these things, what you notice is that many of these earlier components were being done in wind tunnels. That's kind of strange, isn't it? I'm not sure where all our components have gone. Okay, all right, that's bizarre. And so dimensional analysis is something that's typically used to be able to evaluate these. And so last time we talked about the fact that there are these important characteristic numbers. Reynolds number being what? The ratio of inertia to viscous forces. The other one that we're mainly interested in was the Euler number, which is the ratio of pressure forces to inertial forces. These are just ratios of forces. And so the Euler number, as we recalled, was the same as the truck going behind the 747 on San Francisco's runway, is that you stop the velocity against the truck from the jet engine. That applies a pressure, and you see that both pressure and for destroying momentum, the inertia force is just code for destruction of momentum. Inertia is the same as the rate of change of momentum. And from that, we can get some idea of the forces that are applied to structures. So the significance of this non-dimensional analysis or dimensional analysis that results in these non-dimensional numbers is that you actually don't need to know the expressions. You don't need to solve the equations. you can just define the important parameters that you think are that control your particular system. So, turn those on. Is that good? Maybe. And so that's what we'll talk about today, is how we might use individual models. And so it's really quite straightforward. The easiest way to think about it is that in terms of what we did last time, was that we ended up with a behavior that gave us a plot of Reynolds number, which is a velocity, a characteristic length, which was our d, a density, and divided by a viscosity. And we had an Euler number, which is a pressure. So this is P rather than rho. So it's not a very good P, is it? Over rho V squared. And in our particular case, the result we had was slightly different. It had another term involved in it as well. It had this term, which was also for our particular geometry, which was a pipe. It had a length. It had a diameter, which we were using as the characteristic dimension. It had a pressure drop along the length of it. And it had a velocity, an average velocity, which was flowing through it. So this is the average velocity. We remember that the velocity actually has this parabolic form, but we don't really care so much about this. And it had the characteristics of the fluids, which were density and viscosity. So we have all of these terms represented, hopefully, in this. And so what we would imagine is that when we went through our analysis, so we had, what did we have? We had change in pressure over length was equal some function of those properties. A diameter, a viscosity, bless you, a density, and an average velocity. And so what we remember about Buckingham pi, which I guess is up here, is that we have k variables, variables, and in this particular case we had 1, 2, 3, 4, 5 of these. We had r units, if you like, which in our particular case were definitely length. Mass is in density is mass per unit volume, and velocity is length over time. So this was 3, and so the difference between these, 5 minus 3, said that we had 2 pi terms. And it turned out that our pi terms were, one of which was this. Our other pi term, I guess if we go back to the same units, was actually kind of an Euler number. It was change in pressure with a length and multiplied through by a diameter here. So it's kind of an Euler number. It's actually an Euler number that's multiplied by d over L. And so the point is, if we have 2 terms, then if you did an experiment on a pipe, any pipe, we made the point that you'd come up, whatever experiment you did, you'd always end up coming out on the same graph. Any experiment you chose at any particular Reynolds number, we'd come up on the same graph in terms of these terms for the laminar behavior. It turns out that if we look at turbulent behavior, we need some extra, at least one extra parameter. But we could also have done this. So you could imagine that instead of this analysis that we did here, we could have done maybe this. So our parameters could have been change in pressure as a function of what? Same parameters as before: diameter, viscosity, density, velocity. We still have one other characteristic dimension which controls this behavior. So this is just, if this is just the pressure drop over the length of the flow, we could also include the length of the flow in here. If we did the Buckingham pi calculation for this, we have K now is equal to 6. We have R now is equal to 3. And so by definition, the difference of those means we have 3 pi terms. And so if we went through Buckingham pi for this, you could imagine that we'd end up with an extra variable by the fact that we have this term here. And you could imagine that what would come out of it would be that we'd end up with a term which is change in pressure over rho v squared. And that is a function of maybe Reynolds number. And we'd also end up with another term which presumably would account for this extra component that we're not including in this initial term here, and it would be something like L over D, or D over L. And so physically what that means is that now the behavior of our system is controlled by these three properties, 3 terms. And so what the graph then would look like would be that we'd end up with a graph for taking Reynolds number, which indexes the flow regime, the Euler number, which says something about the pressure you have to apply to push fluid through the system, or for instance, if it was a blunt-ended cylinder, where this is actually blunt and the air is flowing over it, it would give you a magnitude of the pressure that you build up here by killing the velocity, and therefore it would say something about the force that you'd have to apply to hold this thing in place. Just like resisting a car, you know, the force you have to apply to push a car through air. But because it has 3 pi terms, then this component for this would be for length over diameter equal 1, length over diameter equal 2, length over diameter equal 10, whatever. And so you'd end up with that as a result of it. So any experiment that you would do would fit on this graph, but now because you have 3 pi terms in this particular case, the graph looks slightly different. And so that's the essence of what we're trying to do. You'd prefer to have experiments where you have the fewest number of pi terms because they're simplest to analyze. But if reality suggests that the behavior is going to be composed of more dimensionless terms than 2, or more than 3 for that matter, then you have to think creatively about how you do experiments. So anyway, it's simple for us to maybe think about the behavior for a particular deal. All right, so how does that relate to what we're talking about now? So what this means is, of course, you could do an experiment with the velociraptor, or whatever the bird was, the 5-winged dinosaur, in the wind tunnel. And you might like that to be able to represent the real case. So we're going to talk about a model, see if we have enough space here, and either the real case or the prototype, whatever we want to call it. And so if we want to do these experiments and to do them in a meaningful way, we actually have to use the idea of similitude. And similitude is just a fancy word of saying that it has to be the same as our real physical system. And similitude comes in three flavors. We have geometric similitude, we have kinematic similitude, and we have dynamic similitude. And so let's just zip ahead to be able to say what these are. Geometric similitude merely means that it's a scale model. So in other words, if this is a 10th scale versus 1/1 scale. So the prototype always is 1/, it's the real size of the plane. So if you want to do experiments on a model, every dimension has to be shrunk by a factor of 10. So it has to be, it can't be elongated. You can't shrink the width by 10 but keep it the same length. You have to physically make it exactly the scale. So geometric similitude means that every dimension of the model has to be shrunk or expanded, I guess, in some cases, but usually shrunk by the same ratio. Kinematic means the same flow regime. Same flow regime means that the Reynolds number of the model has to equal the Reynolds number of the prototype. We want exactly the same flow regime to exist. And so there's a little picture showing these, perhaps a bit more clear. Let's not worry about this, but this is the key thing here. So similitude requires that if you're going to do an experiment on something, you have to make sure that you have the geometry is exactly the same. So the model and the prototype have to be the same dimensions. This would not work, right? Because you've stretched the height, but you haven't stretched the width. And so it doesn't represent the same geometry. That's probably self-evident, but it's worth saying. Kinematic similitude means that the flow regime has to be exactly the same around it. And this physically means just that the Reynolds number are equivalent. This is Reynolds number of the prototype. This is Reynolds number of the model. And so the average velocities that you have in the system scaling with the, so is it velocity, density, some characteristic length, doesn't matter what that length is, and viscosity. So conceivably you could imagine doing, we made this point before when I was talking about the self-bailers. A self-bailer, of course, bails water out of a boat by flowing past the underside of the boat, creating a vacuum, a Venturi effect, and sucking the water out of the boat. You could figure out how that worked just by blowing air across the top of it and measuring the change in pressure underneath it with a manometer. So in that case, you'd be using a different viscosity in the in your model, bless you, than you would be in your prototype. And that's perfectly admissible. So long as the flow you have around your model was exactly the same Reynolds number, it's absolutely admissible that you do that. Okay? So geometric similitude, kinematic similitude, and then if you have those things both satisfied, then if you measure the forces which are applied on a structure, either the shear force or the force just by killing the velocity here. So in other words, you'd imagine that here we have a pressure applied by killing this velocity. So the force has to equal this pressure times the area. Then you'd like to be able to relate that to this. And so dynamic similitude, for most of the cases that we'll talk about, means that the Euler number of the model, which is the pressure that you generate somewhere multiplied by the density of the fluid and an average velocity, has to equal, and this is of course for the model, has to equal the Euler number for the prototype, which is the pressure that's applied on the prototype divided by the density of the fluid, the velocity squared. And that's it. And so if you're typically, these properties of Reynolds numbers and Euler numbers are the ones that you want to use. Not always. If you have a creeping flow where the forces are devised by viscous behavior, then it might be different. But for many of the circumstances we'll deal with, it's useful for us to think in terms of that. And so that's basically the idea. And so what that suggests is that you could do an experiment with our dinosaur to be able to figure out what the forces would be applied to that. And it's pretty straightforward. Okay? I've lost my little thing here. That'll get me out, I think. Don't know why I can't find, don't know why it's not doing that. What do I want to do? All right, I'll do this then. I will do, I'm looking for my piece of paper to write on. It's not that. It's not that. It's this. Okay, so I don't know why that is gone. Anyway, so fine. Sorry for the interlude. So, all right, so let's do something with this. So we are 9. Very good. I realized that might be coming up when I said that. Very good. So dimensional analysis. So let's do this. So we've got our velociraptor. I'm not sure what it is. Some 5-winged bird in the as a model, and we've got the real system. Let's call it real and model instead of prototype. And the real is this is the wing, and let's say the wing is d by L. Let's say L is equal to 1 meter, and let's say d is equal to 1/10 of that. Okay, so we don't have a wind tunnel that can take it, so we make a model which is a 1/10 scale. So that means that the L of the model is going to be equal to 0.1 meters, and the D of the model is going to be equal to 0.01 centimeter. So it's going to be a centimeter wide, the wing, and it's going to be 4 inches long. 10 centimeters is 4 inches. So it's basically the size of my pencil. So not perhaps you expect the web of the wing maybe to be longer, but it's just easy if we use multiples of unity. So the basic idea is this. We can go into the wind tunnel with our model, and we can do an experiment which gives us the Reynolds number, a particular Reynolds number, which is a velocity, a density, and a length, characteristic length. You could choose either L over D, it doesn't really matter, and the viscosity. And so with our model, we could do a bunch of experiments, and we could measure the pressure that's applied on that. And then if we measure the pressure and plot the pressure that's measured as a function of the density of the fluid that's flowing and the velocity of the fluid that's going past it, we get an Euler number, right? So you put it in the wind tunnel, you measure, how would you measure pressure? The easiest way to measure pressure, as you saw, it was upside down. I don't really know why it was upside down. I guess maybe because, I guess it's easiest, right? So it's hanging upside down. You have air flowing across it. You expect it to have some lift, so the lift will pull it down. And so the lift will just extend those hangers, and you measure the change in force in those hangers, and that gives you the effective force, that's the lift force. If you divide that force by the area of the wings, you have the pressures on the wings, right? So that's how you get the pressure. And so imagine this is hanging upside down. We measure the force that's applied here, the change in force, and that gives us a change in pressure multiplied by the area. We know that the area is equal to the web of the wing multiplied by its length, and so we know all these things. We measure this. We know this from our geometry, so we can calculate P. We can plot P. We know the density of the fluid if we choose to use air, and the velocity. So you do it at one particular velocity, that's one Reynolds number, you end up with 1 point. You do it at a second Reynolds number, you end up measuring a different force, second point. Third Reynolds number, different magnitude, and you have a curve. And this is for our It's for our one-to-one model, right? It's the same geometric model as any others. So we have this curve. Actually, we don't really need to do that. What this is saying is now, if we go in, and I wish I had a different color here, so these are the calculations for the model. It'll be the same behavior for the real prototype as well, except the prototype is going to be flying at a real velocity, which may be a different Reynolds number. And if we go across here, whoops, it moved something, right? If we go across here, then this would be the appropriate Euler number, which would be for this case. So this is the concept that you can do a whole bunch of experiments and get a curve and plot against it. But actually all we really need to know is that we're satisfying each of the similitude requirements. And so what were they? They were geometric. And so all the dimensions are one-to-one. One-to-one. In other words, the length of the model divided by the width of the web of the model is equal to the length of the real case divided by the web of the real case. So that's clear. So it's a scale model. So that's the easiest one to satisfy. We want to satisfy kinematic. Is that what we called it? Kinematic similitude. That is that the Reynolds number of the model is equal to the Reynolds number of the prototype. And so we could do a whole bunch of experiments with the model to get this curve, or we could just do one experiment that is actually at the right Reynolds number for both of these. And so what are we going to do? So maybe we think that this, what did I put down? Maybe we think that the bird flies at a velocity in the real case of 10 meters a second, which is about 20 miles an hour, factor of 2. So if we're doing that, then if we want to make this work, then we know that the velocity times the length times the density of the model times viscosity has to equal the velocity, length, density, and viscosity of the real case. If we're using air in both cases, we don't have to worry about these. And so the result of this is that the velocity of the model should equal the velocity of the real case, multiplied by the length of the real case divided by the length of the model, which is just velocity of the real case. Length of the real case is 1. Length of the model is 1 over 10. Equals 10 VR. So in other words, the model velocity is equal to 100 meters a second. So to satisfy this kinematic similitude, I can't actually get out of this. I think it was kinematic, right? Geometric, kinematic, and dynamic. Doesn't matter what the terms are. But we have to satisfy that the flow regime is exactly the same. So if we do our model experiment at 100 meters per second, we're guaranteed to be on exactly the same line as this. And so I'm trying to think, yeah, dynamic is the final one, right? I actually have written it. So dynamic similitude requires that the Euler number of the model is equal to the Euler number of the real one. And so in terms of these properties, the Euler number is the pressure, divided by the density of the fluid and the velocity squared of the model, and it has to equal the pressure, density, velocity squared of the prototype, or the real one. So we can certainly measure this one. This is what we'd measure in the wind tunnel through the forces. The densities of the fluids are the same that we're using, and so we could simplify this as, what do we want to get out of this? We want to know the pressure in the real case. Pressure in the real dinosaur would equal the pressure measured in the model multiplied by the velocity squared in the real case and the velocity in the model squared. And so, if in this experiment we measured on the model that the force applied was 1 Newton, no idea what it might be, then what would the pressure be? The pressure would be equal to 1 Newton divided by the area. So in model, force is equal to 1 Newton. We're just assuming that, just a nice number. Then the pressure would be equal to what? It would be equal to force over area, which is equal to force divided by length times the web thickness. And this is for the model. And what are those numbers? So 1 Newton divided by length was 10 to the minus 1, and the web was 10 to the minus 2 meters squared. So it's 10 to the 3 newtons per meter squared. So you might not be able to see this. This is plus 3. Right? 1 divided by 10 to the minus 3. And so the pressure that we measure on this wing by doing this experiment would be equal to this. And so from this, if we now take this and substitute into here, we have the pressure in the real case would be equal to 10 to the 3 newtons per meter squared multiplied by the velocity in the real case squared, velocity in the model squared, and this would be 10 to the 3. This is a dimensionless ratio because the velocity in the real case was 10 meters per second, and the experiment we did was at 100 meters per second. And so this is going to be 10 to the, this is basically the ratio of these is 10 to the 1, so 10 to the 1 squared is 10 to the 2. So is that 10 newtons per meter squared? It comes out to be the same, is that right? Or am I doing something wrong here? I guess that's the pressure. Is that right? Yeah, so I think it is. So the real case was 10 meters a second. The model was had to go at 100 meters a second for Reynolds number similitude, kinematic similitude, and so that's 10 to the 1, 10 to the 1 squared is 10 to the 2, 10 to the 3 over 10 to the 2 is 10 to the 1. And so that's the pressure that we'd applied. So presumably now, if you know what the pressure is on the real case, if you know what the density of this bird is, and they can calculate its weight, and now you can figure out whether the lift is enough to be able to lift it. That's basically the goal of this, is you want to be able to know whether there's enough lift to be able to take it off. And so you could now do that calculation from doing this experiment in the wind tunnel. So that's really all that it is. So you have to satisfy these 3 requirements. You have to be able to make sure that the model is one-to-one similar. You have to make sure that the flow regime around the model is the same in the model as it would be in real life, because that will define whether the forces are replicates of the real ones it would see. And then if you do that, then you can calculate the forces typically from an Euler's number in some cases, and to be able to do that. Okay? So that's really what Buckingham pi can be used for, dimensional analysis. Very powerful technique. There are some examples here. Won't go through the rest, but just point them out to you. This is one exactly the same kind of idea as what we've done, and that is to calculate the forces applied on a satellite dish by doing the experiment in air. And so the idea is, how do you do that? Well, you make a satellite dish which is a model of the real one at some scale. You flow air past it. You make sure that the air going past it is at the same kinematic relationships, in other words, Reynolds numbers equivalence. And then if you measure the forces that are applied on the model, you can use those to scale up to the other one. So here, the steps are this. Reynolds number similitude means that the Reynolds number for the model has to equal the Reynolds number for the prototype. So this new, we've never used this, but kinematic viscosity is equal to dynamic viscosity divided by density. And so this is just the Reynolds number. If you substitute it in here, this expression here, this would be the same as mu over velocity times density times d. So this is just using a viscosity which includes the density, just a different way. This is called kinematic viscosity. Rather than dynamic viscosity. So we've never used this, but that's all it is. So you seek Reynolds number similitude. So in other words, you choose the velocity in your model, given that you know what your model dimensions are and the model fluid is. In this case, it's air and air, so we get rid of these. You know what your real diameter of your antenna is. You know what your model diameter is. You know what the real velocity is that it's going to see in reality. And so you scale your experimental velocities to do that. And so you calculate what that is. Once you know that, it turns out in this particular case that the scaling is 1-to-1. Once you do that, you calculate what the magnitude of the sorry, that's not scaling. That's the viscosities are 1-to-1 because it's air in both cases. You calculate the velocity scaling just as we did for our model. It comes out to be, in representing a real case, which is 80 kilometers an hour, which is the real wind speed. Sounds about right. It's about 50 miles an hour, right? So to do the experiment, we actually need to do a faster velocity because it's a smaller diameter model. So you do your experiments at 400 kilometers an hour in the wind tunnel. Once you have that, then you look at Euler number similitude. So in this particular case, the drag force that's applied by air going around this is this uppercase, this squiggly d. So this is drag force. So drag pressure, if you like. Drag pressure P would be equal to the drag force squirrely d, bad choice of terms in this, divided by pi d squared, right, an area. This is pi. And so d over d squared is this term here. So this term here is just the pressure. Pressure over rho v squared, halves don't matter. Turns out that we'll talk about flow around external bodies, and because of the half v squared over 2g term, this half is often left in here, but it obviously doesn't matter in this particular case. But this is Euler's number, right? This is kinematic similitude. This is dynamic similitude. We measure the drag force on the model. We know the diameter of the model. We're running the model at 400 kilometers an hour. We're running it in air, so we don't care about these. We can calculate then the behavior at 80 kilometers an hour for the real size dish, and the only parameter we're left with is the force that's applied. And we want to know that force because we want to make the column strong enough that it doesn't snap off. This would be the real reason for doing that. And so as a result, in this particular case, it comes out to being actually the same as measured in the model, just by happenstance, but not always the case. It's the same in this case because the scaling here is just the area of this thing. So I guess you could guess that the scaling would come out to be the same if the thing that you're measured is equal area. So in other words, it's as high as it is wide. In our case with the wing, the scaling wasn't the same because it was one dimension was longer than the other, and so the areas didn't match up. But that's basically the idea. And so that's really probably all I wanted to say today. So take-home message is we don't need to be able to solve the Navier-Stokes equations to be able to do this. We can, if we know what the physical parameters are which control our system, we can say something sensible about what the relationships would be that would link the behaviors in a model and a prototype scale. There is a formal way to do it. It's called Buckingham Pi. It means that we isolate the individual parameters that define our behavior and go through a recipe that allows us to define these different non-dimensional variables. If you choose different repeating variables and different primary variables, you do end up with different dimensionless groups. And so for the purpose of tests and exams and problems, to make grading easier, we always say use these as repeating variables and use these as the non-repeating variables, because that defines that you get unique sets of groups out of it. For most of the systems that we'll deal with, if we're satisfying similitude, we need a model that is scale 1-to-1 in all the dimensions, but can be just shrunk uniformly or expanded uniformly between the prototype and the model. To satisfy kinematic similitude, we need to have the flow velocities satisfy the right Reynolds number, which is the index of whether the flow has the same number of vortices coming off it or whether it's a creeping flow. And then if we satisfy both of those requirements, geometric and kinematic similitude, then if we measure forces on the model structure, we can typically apply those forces to the real life structure by being able to just use the Euler number, typically for the problems we're looking at. It's not always the case that we can do that. If you look, for instance, at the example before this, it deals with flow around a washer where it's a viscous flow. So the flows that we've been talking about are all the natural pragmatic flows where you have air hitting your chest out of the jet engine, or a hose turned on someone, or the jet lev. All of those are flows where the force is made by destroying velocity. In some cases, very slow flows, for instance, dropping a bead into treacle, the rate at which it falls in treacle, which is used actually as settling velocity to actually do grain size distributions when you're trying to figure out what the grain size distribution is of a soil. You measure its rate of fall, and from that you can calculate what the diameter, the grain diameter is. That is not controlled by the pressure developed on the front of the grain as it speeds through this liquid. Rather, it's the shear stresses on the side of the grain as the viscous fluid flows past it, or it flows through the viscous fluid. So in the cases where that is the case, which is the case for this one, a viscous flow around a plate, then you'll note that the viscosity is in here, but nowhere in here do you see the density. The density would be the Reynolds number equivalent. So this is assuming that the flow is at a really low Reynolds number may be less than 1, in which case the density has no impact on this. And so, that's a judgment call. But you notice in this case that the force that's applied on the washer is now a drag force, which is not quite the same as the Euler number, right? It varies with viscosity, velocity, and some characteristic dimension. You can check this out. It should actually be a non-dimensional parameter, and it varies with the geometry of this. And so it's not always the case that geometric similitude, kinematic similitude, and dynamic similitude means geometry matches, Reynolds number matches, and Euler number is the one that we need. In some cases, the final step in terms of the dynamic similitude might be another parameter. And in this particular case, it shows that's the case. However, in most of the examples that we'll deal with, it's usually Euler number. We'll talk about flow in pipes next, and that definitely is Euler number controlled. We'll talk then about flow around immersed objects, wind turbine blades, forces applied on rounded water towers in State College. In those cases, it's again Euler number similitude to give us the dynamic behavior. Okay. I'll finish there. Thank you very much.